Hello everyone, this is Ishtiaq. I'm currently a final year PhD candidate at Virginia Tech, uh, and I'll be presenting our work from diagnosis to repair, a large-scale study of DNSSEC misconfigurations and an automated error resolution framework. The other authors in this work are Dr. Olivier from University of Grenoble, Dr. Casey from Brigham Young University, and Dr. TJ Chung from Virginia Tech. So we all know that DNSSEC is really important, but its adoption rate is still really low. The reasons that have been identified in the prior works are generally that DNSSEC is really complex. There is deployment of DNSSEC is difficult. There is post-deployment maintenance challenges, operational challenges such as lack of register support, and then of course there is a lack of incentive for the domain owners to deploy DNSSEC. In this work, we want to address the complexity part of it. Using an automated tool, we want to find out whether we can reduce the complexity of DNSSEC, especially the post-deployment complexities of DNSSEC. So before diving into our work, let me briefly introduce a tool that is widely used for DNSSEC analysis called DNSViz. I guess many of you already know about this, but if you don't know, DNSViz is a diagnostic website or tool widely used for DNSSEC analysis. When you input a domain here, it analyzes the DNSSEC configuration of a domain and then gives you a rich graphical visualization to pinpoint and then pinpoints where the exact error is. It also gives you a specific set of error codes and outlines the errors, as you can see in the left-hand side of the figure. And it has a CLI version as well that you can use in your own local environment to test your DNSSEC setup or your domain's DNSSEC setup. Okay, we have got around 1.1 million total snapshots from DNSViz as our dataset. What is defined as a snapshot is basically an analysis of a domain at a specific point of time. And we have 1.1 million of them spanning from March 2020 to September 2024. These snapshots belong to around 319K SLD and beyond domains, unique domains, and among them 84K of these domains have at least 2 snapshots. Okay, now our objective is to understand the DNSSEC debugging pattern from these snapshots. So first, to do that, we want to first categorize the snapshots in 4 distinct categories. The first one is silent valid. Silent valid are those snapshots that have no DNSSEC errors. So every signatures in the snapshots are actually current and verifiable, and a validating resolver would be able to successfully authenticate all the queries present in the snapshots. That's called silent valid or SV. Silent valid but with misconfigurations, or SVM in short. The category, this snapshot basically means that there are some DNSSEC errors present in this snapshot, but generally these errors do not cause server fail. So for example, non-zero iteration count in INSEC tree. Generally, this is a RC violation, but generally the resolvers tend to ignore that and do not cause server fail or do not trigger validation error. So these sort of errors are categorized into SVM category. Then you have signed and bogus category, which means that at least one query, at least one authoritative server of the domain in the snapshot will fail cryptographic validation. So for example, one query, one error sig has an expired signature. So these errors generally produce a server fail response code, effectively breaking DNS resolution for validating resolvers. And finally, we have insecure, which means the domain in the snapshot is explicitly unsigned in a valid way. So there is a confirmed proof of non-existence or non-existence of a DS record that resolvers can recognize. So these are the snapshot categories. We also would like to categorize the domains that belong to these snapshots. So we categorize them into 2 sets. One is changing domains and one is stable domains. Changing domains means that domains that exhibit at least 2 snapshots with different DNSSEC related error codes. So that differences indicate that something in the DNSSEC configuration changed between observations, whether intentionally, like you have key rollover or DS update, or unintentionally, like expire signatures. We analyze these domains extensively to understand how operators fix or fail to fix those misconfigurations. And then you have stable domains where domains or snapshots all reside in the same DNSSEC category throughout the dataset. Okay, now let's try to understand. Now our objective is to trying to understand whether DNSViz is used by the administrators to fix their errors or correct their misconfigurations. To do that, what we did is we plotted a Sankey diagram for domains in the CD category. the changing domains category, to compare the DNSSEC status between the first and the last snapshot recorded by DNSViz. And we see some interesting things. So we find out that 7,200 of the domains that previously belonged in the SB category or signed in bogus category, they actually corrected their errors and transitioned to either SV or SVM. And 2,400 of the domains that previously belonged to the insecure category, out of 3,907, they adopted DNSSEC. So definitely there is a positive transition, and that means that administrators actually are using DNSBiz to fix or deploy DNSSEC. We also see some negative transition as well. So for example, 650 of the domains that previously were in the SV or SBM category had DNSSEC, disabled DNSSEC, and then 588 of them transitioned to bogus that previously were valid. So we want to explore these negative transitions further. We wanted to see what triggered these negative transitions. So to find out the cause, we looked into the 2 consecutive snapshots that caused these transitions, or that had this transition from SV to SB. And we found out that there are 3 trigger points potentially. One is NS update, where the name server got updated, and that might have triggered this transition. We also see the key got changed, the DNS key got updated. Then you also see the key algorithm got updated in 26.2% of the cases. So this explains the negative transitions, and we also observe the same scenario for SB to IS, so valid, sign-in valid to insecure transition as well, which caused these issues. Okay, so we also want to outline the top errors that we observed in our dataset. So as we can see here, we have specific categories and subcategories. And for example, the missing KSK for algorithm, which means the DS record referencing a DNSK algorithm that is not actually present in the zone, is present in almost 8.4% of the snapshots. That's a significant amount. We also observe inconsistency between DNS keys, of the different authoritative servers of the same zone. We also see incomplete algorithm setup. We see missing signatures and missing non-existent proof errors in 5 and 8% of the cases respectively. And we also want to highlight one of the very prominent errors we see, which is non-zero iteration count in NSEC 3. So in NSEC 3 parameters, in NSEC 3, there's a parameter called iteration count, which has to be 0 according to RFC, but in 28.8% of the snapshots, we actually observed that this is not being mandated. So that's a very prominent error. Okay, so based on all of these findings, we make 2 observations. That despite DNSSEC's complexities, many domains are actually exhibiting the same recurring mistakes. So expired error stick, stale DS records, incomplete algorithm transitions. So the patterns of DNSSEC errors are pretty common. And then another observation is, although DNSSEC provisioning can be intricate, bind, which is a very widely used DNS authoritative server, we're using bind as an example here. Bind uses a very limited set of commands even in the manual setting. So for example, DNSSEC sign zone are used for signing the zone. DNSSEC keygen are used for generating keys. So the repeat of bind commands or repeat of commands are pretty small. So based on these 2 observations, we want to introduce DFixer, which is a semi-automated error resolution framework. Just to give you a hint of how DFixer looks like. So let's imagine a domain that have 1 KSK, 1 ZSK, and KSK has a revoked bit set. So that is the error, DNSSEC error that we want to fix using DFixer. If we input this domain erroneous zone to DNSViz, to DFixer, which is our tool, what it's going to do is going to first identify the root cause behind the problem. The rationale behind root cause is there can be multiple errors residing in a zone, but more often than not, we see dependencies between those errors, and resolving one of them can actually resolve all of them. So we want to identify the root cause first, which is in this case very simple. Your DS record is linked to a DNS key that is revoked. And then DFixer comes with a specific remediation plan with exact commands as well. So for example, if you look at the first step here, it says generate a new KSK key pair using and execute this particular command where you have to replace the variables with your own environment variables. And then it gives you a set of instructions to follow that you can follow one by one to make sure that your zone is resolved. Okay, now that we have an idea of how DFixer looks like, or how DFixer output looks like, let's dig deep into DFixer and look at the pipeline. So what we do here is we use DNSViz CLI to first extract the errors or analyze the zone using DNSViz. So from DNSViz CLI, we basically extract a JSON format analysis from DNSViz that has a specific set of errors and identifies which errors are present. We parse this JSON in second step. We parse this JSON, we extract the errors, and we sort them topologically. Again, the rationale is the errors are dependent, so we want to resolve the independent errors first. And then we get the topmost error, we map it to the root cause, and then we create a remediation plan to fix that error, and we map those plan to commands as well. That's that module. This module is called the resolver. And then finally, step 4, which is an optional mode, optional auto application mode, DFixer can automatically apply those commands in your environment and then go back to step 1 until all the errors are fixed. So this is an iterative remediation process, and this process repeats until no blocking errors remain. Okay, now that we have built DFixer, how would we evaluate it? That's a problem. But remember that we have a lot of erroneous zones from DNSViz from the past, right? Can we recreate them in our own environment? Can we create a synthesized zone in our own environment, replicating those same errors? That is the motivation of our new tool that is we built called zReplicator. Our idea is we will inject the exact misconfigurations present from the DNSViz logs. We will run DFixer, apply suggested commands by DFixer, and confirm that the zone is resolved. So how we do that? We first create a base zone, fully signed bind zone as an SLD to serve as the root of our local environment. So this enables us to automate communication with the parent zone during evaluation. Then we create subzones to emulate the parent and child zones, mirroring the parameters. So for example, the number of DNS keys and their flags, the algorithms, key size, number of DS records, digest type, usage of NSEC versus NSEC tree, all of them will be exactly mirrored to make sure that we actually emulating the target zone. And then finally, we try to inject the DNSSEC errors present there. For example, if you have an invalid DS digest, we will perturb the DS records, or we will perturb the characters inside the DS records to make sure that error pops up. Okay, we want to evaluate DFixer, right? But we also want to evaluate our zReplicator tool as well. So to do that, we have come up with 2 metrics. One is replication rate, which identifies how comprehensively we can recreate real-world misconfigurations. And then we have a fix rate, which outlines how accurately DFixer resolves DNSSEC errors. And this is the result. If we go back, if we recall the error distribution, you remember that we have a very highly skewed non-zero iteration count error. So not to skew the results, because fixing that is really easy, we divided our result into 2 subsets. One is the snapshots that have only non-zero iteration count error, and one is the remaining subset with more complex combinations of errors. And as you can see, we have around 79% replication rate and almost 100% fix rate. So that's a very high fix rate, also a very high replication rate as well. For the zones that we could not fix, the DFixer could not fix, it was because the parent zone had errors. So the parent zone had to be fixed first before you come up to fix the child zone. These are the top set of instructions that are issued by DFixer in its iterative remediation process. We see only iteration up to 4, so that means DFixer is pretty efficient. And then, as expected, signing the zone is the topmost instruction, followed by removing the incorrect DS record and uploading the DS record. So to discuss, there are some limitations in our zReplicator tool specifically. So some of the complex negative proof errors are not reproducible, so we cannot replicate them. We only replicated leaf zone, so that means there are some complex combinations that zReplicator could not replicate, and this is the reason why the replication rate is a little low, 80%. And then the only limitations of DFixer is we could not automate the updating procedure of DNS recording register. So that has to be done manually. We could have used CDS or CDNS key, but that is not widely used, so we didn't use that. And finally, we also checked the extensibility of DFixer to other DNS software, and we found out that it is actually extensible. So you can use it to NSD and Power DNS as well. But to be honest, it can be extended to any other software that has those signing commands. So thanks a lot for giving me the opportunity to present our work here. And if you have any questions, feel free to reach out. Thank you.